Hi everyone. Today we're going to continue on 4.2. So if I remember correctly, the last thing we talked about was try to understand when we have a real value function, several variables, what would the graph of those functions be? So I showed you that when you have a function that went from R2 to R, it would be a two-dimensional surface in R3. The word surface is more like a catch-all term for um, all the object that's created by this type of function. Excuse me. In the same way that the word plane, which our basic perception is two-dimensional, but actually could have higher dimension plane in higher dimension. So here's the same exact concept. Now, if this concept still confuses you of why thinking of them as like surface, then once we talk about how the graph is being drawn, then you probably hopefully make more sense. But when you have a function made from R2 to R, we call that a two-dimensional surface in R3, which is basically just a regular surface that we're comfortable with because it's in R3. But if you have a function that made from R3 to R, there will be a three-dimensional surface in R3. While it might be tempting to think a three-dimensional object is more like a solid, the problem is that because this three-dimensional object actually exists in R4, and therefore it actually have more similarity than a surface in R3 than a solid in R3. Okay, so therefore this, which is the reason why I call it a three-dimensional surface, because geometry-wise it actually behaves more like a surface than like a solid. As a matter of fact, in R4, we'll likely only call something fourth dimensional, which is like R4, to be called solid, just like we only refer to something three dimensional as a solid in R3. But things that are less dimension, we usually use the catch-all word of surface to describe them, unless it's one dimensional, where we would use curve or path to describe them. Now, one way to try to understand how all this graph and surface work is to actually try to understand the basic mechanic of how we draw a graph with this type of function first. And lucky for us, these are the type of function, explicit function. These are the type of function that you have learned how to do for the past like 5 years when you first learn about drawing graph of a function. So therefore, it's not something difficult that we cannot figure it out. So we can actually come up with this, the concept of it. So let's see. So let's try to examine how we draw a graph, a basic function first. So let's start with something like this. Let's say we're going to start with f that met from R to R. So these are the type of function that you have learned how to do back in, I say 7th grade. And let's pick a very easy function so we know what the graph looks like. F of x equal to x squared. Okay, now without even doing anything, we already know what this graph is. This graph is a parabola. It's a parabola on the xy plane. So therefore, you know that this function would generate a curve in R2. It's just that we didn't use that kind of terminology before when you first learned about it. But now that we have this kind of terminology, we can now using this terminology, this type of terminology, to now expand to higher dimension. Okay, but we know it is a parabola on the xy plane, which basically meaning is a curve, and the xy plane is technically just R2. Now let's try to understand the basic mechanic of how to draw this graph. Okay, so now let's try to draw the graph. So we all know how to draw the graph. So here's my x-axis, here's my y-axis, right? And then here how the graph look like. Then we'll label it. Nope, actually, oh yeah, I guess I can say y equal f of x, which is equal to x squared, I guess. Okay, right? That's pretty simple, right? But let's try to understand how we did this. So think of the following. Ready? So first thing I notice is the following. In this graph, we name the horizontal axis x because that is the domain. And then we name the vertical axis y because that is the range. And then our graph is technically the image of our equation. Okay? So that makes sense. And the idea is that you have to represent the domain, and then you have kind of the range go off in a different direction, or in this case, in the perpendicular direction, so that we can kind of draw the image that's a combination of what's in the domain and what's in the output, the range. Okay, so that makes sense. So keep that in mind, that we draw the domain and the range perpendicular to each other. Number two, let's say I identify this one point right here. Let's say I identify this one point, which is, I don't know, 2, 4, let's say. Okay, let's mark that. Let me do this. Oops. Okay. Let's say this is the point 2, 4. So how do we come about recognizing this point as 2, 4? Well, simple. Is that we first identify 2 in the domain, and then recognize that the output of this function is 4. Therefore, we move it up 4 to get to the point 2, 4. So notice the way we generate our graph is first by identifying the input value in the domain, and then take the output value and translate our point from our domain along the range direction, and therefore identify the point that we need. And that process is repeatedly being applied in order to draw this curve, meaning if I now pick the point 1, it would now go up by 1. And then 0 doesn't do anything, but I pick the point -1, it will now go up by 1 to this point. If I pick -2, it will go up to this point. -2, 4. And not. So therefore, the general idea of drawing the graph have the following properties, okay? The range perpendicular to the domain, number 1. Number 2, identify the input and then translate along the output direction to identify, to find the point that we need. So those are two basic concepts of how we draw a graph. So now it makes sense why our output is a curve. Because essentially what we're doing is basically taking the entire domain, which is this horizontal line, and kind of lift it up to form this curve. So therefore, important to understand is that the image has the same dimension as the domain. Okay, that makes sense in this case because our image is a curve, which is basically a translation of every single point on the x-axis upward to wherever it should be. Or well, technically speaking, it could be downward, but in this graph, it's all moved upward to form the parabola. So now that we have understood some of the basic concept of how to draw this graph, now we are ready to talk about what if we do a graph that met from R2 to R. Now we can try to understand it. So now let's say we're given a function f that met from R2 to R. So first of all, let's not try to figure out what function it looked like, but I will define it this way. Okay, I will define it as f of xy equal to z. So in this expression right here, x and y are independent variable, and there are two of them because our domain is in R2 And then z is our dependent variable. As a matter of fact, for most of our problem, we will kind of choose z to be the output and x and y being input when we have a function that map from R2 to R. But not always, so don't get too caught up with that. But for the most part, we will try to do that. Now, what is this graph going to be? So remember, it is a two-dimensional surface in R3. Or if you want to, you can simply refer to that as surface. It's a surface in R3. Okay. Higher dimension surfaces, we will identify the dimension, but two-dimensional surfaces is just basically surface. So now let's try to follow what we learned. So we're going to try to draw this graph following these three rules that we noticed. So number one, the range has to be perpendicular to the domain. So in this case, what would happen is we will basically form our graph this way. We will have our range, which is our z-axis. And our domain now is x and y, and therefore form the xy plane. So the xy plane is the domain. And then the z-axis would act like the range. And they are perpendicular, so therefore we form a R3 space, which is exactly what we identify from the problem. Good? And now the next thing is, how do I generate this graph? Well, the way to do that is the following, is to first identify a point in the domain, so therefore will be x and y, and then translate it up or down based on the value of the function to identify a point in the image, which is technically speaking, say the output is z. And how do you actually generate the graph? Well, by repeatedly doing that for every single point in the domain. And therefore, every single point in the domain will move up or down, technically speaking, or doesn't move, depending on what the output value is, to its new point. So therefore, now it makes sense that the image would be a surface, because technically the xy plane is a surface itself. And just basically every point on this xy plane, on this surface of xy plane, will move up and down to form some kind of curved surface. So one of the big difference between the word surface and plane is that plane is a surface that's completely flat, while surface can be flat or can be curved. All right. So that's how that whole idea works. So in this case, the image, is a surface which is two-dimensional because it is more or less, quote unquote, a translation, now not technically speaking a true translation, of the domain, which is R2, and therefore also two-dimensional. Okay? Now, maybe give you a more specific example to try to illustrate how this works. How about we try to evaluate a function and see? How about I give you this? How about let's say we let f of xy equal to, I don't know, 1 minus x minus y squared. Okay? And I'm going to ask you to graph the points f of 1, 2. Okay? So let's go and try to do this. So here we go. So I do know that has to be in R3. Why? Because function f map from R2 to R. Therefore, it represents a surface in R3. So how do I actually identify where the point f of 1, 2 is? Well, it's very simple. You first identify 1, 2. And then now let's figure out what f of 1, 2 is. F of 1, 2 would equal to 1 minus x minus, or 1 minus 1 minus 2 squared, which is 4. So 1 minus 1 is 0, so therefore it's negative 4. So therefore what you do is you basically take this point and you kind of count down 4. And now you can identify this one point. There you go. That is the point negative 1, 2, negative 4. Okay. Now imagine I repeatedly doing this process. Then every point on the xy plane will now become a point somewhere up or down, and they will connect together to form a surface. And that's the surface that we're going to try to figure it out. Okay. So then the question comes down to how are we actually going to draw this surface? So one way to actually draw this is to use a method called level set method. So what does it mean by a level set method? So a level set method is a way to draw, technically speaking, you could use it to draw any dimensions graph, but then obviously high dimension will be much harder to do. So we're very likely using it to just generate surface in R3. And yes, I know some of you probably already thinking you will be asked to do something like this on your next test, where you're going to try to sketch a surface in R3. Okay, so show you what you need to do. Okay, so there's several things I want to show you. So let's start by defining what is a level set first. So a K level set of the graph f of vector x is basically the graph of f of vector x equal to k. Now, here's something interesting that you have to pay attention to. The reason why is because, just like what I keep telling all of you, you have to pay attention to the dimension that you're working with so that you make sense, so that you can make sense of what you try to do. So imagine the following. Imagine f mapped from R and to R. Then we call f represent an n-dimensional surface in R n plus 1. Okay, now however, here's the interesting thing. The level set of f is actually a graph in Rn only. Now, why? The reason is simple. Because the reason why f represent a surface in Rn plus 1, because you have n independent variable plus 1 dependent variable, and therefore give you n plus 1 variable total. But a level set doesn't have an output variable. The output is actually fixed as a constant. Therefore, it means that you now no longer have to have the plus 1 dimension that you have to worry about. Now, it might sound very confusing, but let's give you a very simple example. Example, if f mapped from R2 to R, then f represent a 2-dimensional surface in R3. But the level set of f is a graph in R2 only. Now, it might be hard to see why, but if I show you an example, you will be able to see it. So let's see, we can do an example. Let's try this problem right here. Okay, maybe I should say for example instead of EX. Oops. Okay, let's try an example right here. Let's say let f of x, y equal to x squared plus y squared, and I'm also going to define the output, which is z. Okay. Let's see, we can try to generate some level set, and let's see what do they actually do. Okay, so I'm going to ask let's try to generate the following level set. Let's try to generate the level set, the k level set of f, where k equal to, and we'll pick some random numbers. Okay, now obviously I don't randomly choose these 4 numbers, so there's a reason why, but show you. Okay, so let's see, we can generate these level sets. So let's start with the first one, 0 level set. So what does 0 level set mean? Well, it implies that f of xy is equal to 0. That means x squared plus y squared equal to 0. So now comes the big question. What is x squared plus y squared equal to 0 look like? The first thing I notice is the following. Notice there are only 2 variables involved. That means that this thing is in R2. Okay, and notice that there's no parameter involved in this equation, x squared plus y squared equal to 0. So therefore, indicated what we have must be a curve in R2. Why? Because there are only 2 variables. There's no parameters, meaning that one of them must be an independent variable. The other one must be dependent variable. So therefore, this equation, technically speaking, represents some kind of function that maps from R1 to R1. And we already established that function that maps from R1 to R1 is circle. Is a curve. And as a matter of fact, a lot of you already know what this equation look like. Is x squared plus y squared equal to r squared. It's the equation of a circle. But since r squared is 0, therefore we have a 0 radius circle. So therefore the graph of this level set is just the point origin. Now let's see what happens as I move into a higher level set. Notice that k equal 1, 2, 4, 9 is kind of like you raising up the level from level 0 to level 1 to level 4 to level 9. Okay, so one level set would be f of xy equal to 1, therefore x squared plus y squared equal to 1. And guess what? X squared plus y squared equal to 1 is a circle. Radius 1. Now hopefully you realize why I use 4 as the next number but not 2. Because look what happened. F of xy equal to 4, that means x squared plus y squared equal to 4. And that form a bigger circle. And now 9 level set, which will be f of xy equal to 9. So x squared plus y squared equal to 9, and therefore we now have a bigger circle. Now notice that in this case the level set actually form the same kind of curve, but except that it's kind of different sizes. And for the most part, that usually would happen unless some weird function they have some weird level set. Otherwise, the level set tend to form the same kind of shape. So now the question comes down to, what do we do with the level set? Well, this is what we do. The level set kind of give us how the surface will look like if I were to look at it from top down. So therefore, meaning if I look at the XY plane from the Z direction straight down, I would see this circle closest to me, and then this circle further away, and this one even further away, and then this is at the bottom. Now why? Because I'm looking at it from the positive Z direction, and therefore the 9 level set definitely will be a lot closer to me than the 4 or the 1 or the 0. So therefore, if you think about it from the top-down view, so the top-down view of our function would look something like this. With this being the 9 level set, this being the 4 level set, this being the 1 level set, and then you have the 0 level set. Okay? Now come the next question. How would that look like if I'm not looking from top down? Well, that would look like this. Oops. Okay, this picture will look something like this. Maybe I go a little bit over here. Okay, it looks something like this. Here's Y, here's X, here's Z. Let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would account for 9 different level sets. So here we go. The first level, the 0 level set just needs 1 point. 1 level set would form a circle that go around at level 1 level set. And then the 4 levels, so up to 4, and we'll have a bigger circle. That is our 4 level set. And this is our 0 level. And then 9 level, we have an even bigger circle. So now comes the big question. What would this surface look like if I were to be able to complete all the level between each of these? So therefore, kind of have a way to form the surface together. Well, my time kind of ran out, so we're probably going to have to finish it up tomorrow. So only a little bit more left, but I really don't want to make my video too long. So I'll probably going to continue that tomorrow. But one thing I do want to point out is the following. Each of these are circle, not this. Now, how is that different? So you probably remember learning in BC Calculus what we call this method. This method is a solid two-dimensional object, like a CD. Here is not. Here they are just a curve, a circle. So therefore it's only a ring. So therefore if I were to actually draw all of these together and form a surface, it actually wouldn't be hollow inside. It actually won't have anything inside. Okay? It would just be a surface that separates what's outside the surface with what's inside the surface. But it would not be a solid, and there would be no volume to speak of, but there would be area to speak of because it's a surface, so it's similar to like surface area. So keep that in mind. So we'll try to complete this graph tomorrow on the next video, where I will show you something else to help you connect them together. All right, I'll talk to you guys in the next video. Okay, bye-bye.